All right. So I actually had 8.2 and 8.3 ready yesterday, and I started recording this one. And then El Paso Electric decided to do some work in my neighborhood, and the power went off, and I got frustrated. So I'm recording this again. Here we go. Section 8.2 Operations with Matrices. You know how we talked about it earlier, right? There were operations on functions. When you learn numbers, right, you learn how to count, and then you add them, subtract them, multiply them, and divide. And then you learn about fractions, and then you learn about decimals, and you add, subtract, multiply, and divide. And then we had complex numbers, and we had functions. All of these mathematical objects we could add, subtract, multiply, and divide. Well, matrices, right, the matrix, is the same thing. It's a mathematical object. So we're going to talk a little bit about adding, subtracting, and multiplying matrices. We don't actually divide them, but we have a different process. Here we go. A matrix can be denoted by an uppercase letter such as A, B, or C, or any other letter. I know you know what letters are, and I don't care what language the letters are in too. You want to give me some Cyrillic alphabet? Go for it. A matrix can be denoted by a representative element enclosed in brackets. All right, so little aij is the representative matrix of matrix A. Or we could just write out the whole array of numbers. All right, our rectangular array where we have rows, we have columns, everything's organized, everything means something. Excuse me. So two matrices, A and B, are equal. I got to get me something to write with here. If they have the same order and all of their entries are equal component-wise. All right, so as long as I is between 1 and M and J is between 1 and N, the orders, right? For all of the elements, they're equal coordinate-wise. Let's take a look at that. So for here, solve for A11, A12, A21, and A22 in the following matrix. A11 is in the top left position. So it's equal to -2. A12 in the top right position must be equal to 6. A21, second row, first column, A21 has to equal 1, and A22 has to equal 5. All right, so component-wise, row 1, column 1 has to equal row 1, column 1. Row 1, column 2 has to equal row 1, column 2, and so on. That's all that means. Okay, so now we can kind of put this together and find different values, right? A little more creative than the last one. Row 1, column 1 is x plus 2. Row 1, column 1 is 2x plus 6. They must be the same. 5, 5, 3, 3, 4, 4. 2y must be equal to -4. 2x must be equal to -8. 2, 2, 6, 6, y plus 2 must be equal to 0. And so we have 4 equations here. And I solve y plus 2 equal to 0. That tells me y equals -2. If 2x equals -8, x has to be -4. But then I went to the other equations because I have to make sure that these answers work for all of the equations, for all of the x's and the y's in the systems. So 2y equals -4, divide by 2, y equals -2, awesome. X plus 2 equals 2x plus 6. I'll subtract 2x from both sides, and then I'll subtract 2 from both sides. If -x equals 4, then x equals -4, fantastic. We know this is the right answer, we've checked it twice for both x and y. All right, so for matrices to be equal, they have to be like equal, like the same thing in the same positions. Okay, so now let's add them. If A and B are matrices of order m by n, all right, they have to have the same order, then their sum is the m by n matrix given by, and we add these component-wise. We're going to add row 1, column 1 of A to row 1, column 1 of B. Row 2, column 3 of A to row 2, column 3 of B, and so on. This, very important, the sum of two matrices of different orders is undefined. they have to have the same order. They have to have the same size so you could add each component. All right. If A is an n by n matrix and C is a scalar, all right, just some number, the scalar multiple of A by C is, we just multiply every single component of the matrix by C. All right, so that's how we add and subtract, especially if we multiply by a -1 here. Addition and subtraction, essentially the same thing. When we are dealing with matrices, they are commutative. When you add two matrices, you could add in either order. They are associative. As long as you're adding, the order you're adding doesn't matter. Scalar multiplication is associative as well. You can multiply the scalars and then multiply by the matrix, or take them one at a time. Scalar identity is 1. If you multiply everything by 1, you get it back again. And we have the distributive property of scalars over matrices. All right, just a scalar multiplied by matrices. This is not a matrix times a matrix, not yet. All right, so if possible, evaluate. Notice this has 2 rows, 3 columns, 2 rows, 3 columns. They're the same size, so we can add them. I'll take 3 plus a -3. Each one, 1 plus 5, -2 plus 4, second row, 2 plus 18, 7 plus a -6, -9 plus 2. Now, many of you won't need to write this matrix because you could do 3 plus -3 and get 0. All right, so don't feel like you have to write this one. I write it because I'm teaching, right? As you're learning, write it as you need to, and as you get more comfortable with it, maybe you only write this answer matrix because you see where it's coming from. And we add each individual, all right? Make sure we get it. Our negative signs is what kills me most. If possible, evaluate. 2 times, we're going to add 2 column matrices and then subtract a column matrix. So parentheses first. We'll do what's inside the parentheses, and I added the 2 matrices. And you know what I did? I forgot the 2 completely. So right here, I should have had a 2. Right here, I should have had a 2, which means this is 2 times 3. 6 plus 3, that's a 9. Look at me making mistakes. 2 times 3 is 6. 6 minus 2 is 4. Ooh, I could fix that one. 2 times 11 is 22. I just completely forgot about that too. That's my bad. 2 times 11 is 22. 22 minus 6 is 16. Ooh, let's go ahead and save this. I screwed up. Don't forget those 2's. All right, don't forget the steps that are really necessary. I don't know. I'll blame it on yesterday. If possible, evaluate. This time I did remember the 2. This time I multiplied through by 2 first. So I did 2 times every term in that first matrix. 2 times 9, 2 times -5, 2 times +5, 2 times 2, 2 times 1, and 2 times 7. I also multiplied the second matrix by 3. 3 times 1, 3 times -2, 3 times -3, 3 times 7, 3 times 8, and 3 times 0. Now that I've taken care of the multiplications, I can add. 18 and 3 is 21. -10 and -6 is -16, and so on. 14 and 0 gives us 14 on the very last one. It's exactly as we would want it to be if we had to come up with, how do we combine these things, right? It's the most easy way to go. You just add them component-wise. But remember, 3 rows and 2 columns is different than 2 rows and 3 columns. This has a row 3, column 2. I cannot find a row 3, column 2 on this matrix, so I can't possibly subtract or add the opposite. Right? They have to have the same size. Not possible. Now, we talked about how we have coefficient matrices and solution matrices and augmented matrices. Here's how we could use that a little bit. We could solve for x. All right, given A and B, two 3x2 matrices, we have an equation here, a matrix equation. 2x plus 3a equals b. Well, I'm going to subtract 3a from both sides. So 2x is b minus 3 times a. So I multiplied everything in a by 3. It looks like I did it correctly. So I have b minus 3a, that's 0 minus a negative 6, 3 minus a negative 3, and so on. Negative 4 minus 9, negative 13. So if 2x is equal to this matrix, we'll divide everything by 2, this side and this side, to get our matrix x. All right, I did put 3a over here on the side in case you want to see how I got those values. But our x matrix is found. All right, we can find exactly what that matrix is to make a true equation. Don't forget, you could pause. It seems like I'm going through this really quickly, but considering some of the stuff that you've already done, this is somewhat easier. It's different, all right? But compared to the things you've done in chapters 2, 3, and 7, this is you got this. All right, you got this. All right, so we can add and subtract. We can multiply by scalars. How do we multiply matrices? If A is an m by n matrix and B is an n by p matrix, notice different, although the n's matching. The product AB is an m by p matrix, and this is how we find the little fellers. I'm going to show you in particular. So first thing we do is we check m by n, check the size of the first matrix, check the size of the second matrix. If these two are the same, we can multiply. That means it's a go. And this will give you the dimensions of the resulting matrix. All right? M by P is the result. So if the two numbers in the middle match, you can multiply. When you do multiply, the outside values will give you how big it's going to be. Okay, so the number of columns in the first matrix must equal the number of rows in the second matrix. Oh, look, it's that visual right there that I was just trying to do. They have to be equal. The outsides are the order. With matrix multiplication, we still have associativity, distributive property, both the left and the right. Notice the order, however. We do not ever change the order of multiplication. We'll find that AB times BA is not always the same thing. Something that comes up when we're multiplying, right? When you multiply 3 times 1, you get 3. We call 1 an identity. It's nice to have an identity because that allows you to multiply by a form of 1 but not change anything, right? So we have an identity matrix as well. A square matrix that consists of 1s on the diagonal and 0s elsewhere might remind you of Gauss-Jordan elimination. It's called the identity matrix of order n by n. And we abbreviate that as I sub n. An identity matrix must be square. And if we already know, like, we're working with 3 by 3 matrices, we could just call it I because it's assumed to be I3. All right. So let's see an example of this whole multiplication thing. In the first two examples, first one example, I wasn't thinking. I just did it. But the next example is going to show you something. It still makes it easier to multiply. If possible, find AB and BA. Well, A is a 3 by 2 and B is a 3 by 3. To multiply A times B, a 3 by 2 and a 3 by 3, since these two do not match, it's not possible. Can't do it. B times A. B is a 3 by 3. A is a 3 by 2. This tells us that it's possible, and our answer is a 3 by 2 matrix. So we know exactly what to expect. So what I'm going to do, how I'm multiplying this, is I'm going to take this first row and I'm going to multiply it by this first column. So 0 times 2, negative 1 times negative 3, and 0 times 1. Row 1 times column 1 lands in row 1, column 1. And then I'm going to take row 1 and I'm going to multiply it by column 2, and that ends up in row 1, column 2. When I move on to the next one, row 2, Stella says hi. Column 1, row 2, 4 times 2, 0 times negative 3, 2 times 1. Row 2, column 1, when I multiply component-wise and add, that goes in row 2, column 1. Row 3, column 2, I multiply every element in row 3 times every element in column 2, and that goes in row 3, column 2. Hit pause, check them out. Make sure that I've done it correctly, but notice row 1, 0, negative 1, 0, 0, negative 1, 0, 0, negative 1, 0. This row 1 is used in row 1 of the answer. How is column 1 used? 2, negative 3, 1. This first column, 2, negative 3, 1, 2, negative 3, 1, 2, negative 3, 1. There's definitely some patterns going on here. So after we do the multiplication, and that's why these have to match up, right? There has to be three rows of one and columns of the other. Now we multiply. 0 times 2 is 0. Negative 1 times negative 3 is 3 and 0. So 0 plus 3 plus 0 is 3. There's a lot of zeros in here. 8 and 0 and 2 makes 10. 2 plus 3 is 5. Plus 2 more is 7. And the second column, we can find the values as well. A negative 4. 4 and 12 makes 16. 12 minus 4 is 8, plus 1 makes 9. All right, so what I did in the second example, seventh example, now I've used colors. So they're both 2 by 2 matrices. When they're 2 by 2, everything's a 2. We can multiply, awesome. We know our answer is also going to be a 2 by 2. So I put A in green and B in blue. So the row 1 of green and the column 1 of blue, row 1, column 1. Oh, we could do this. Row 1, column 2 is in row 1, column 2. So each time it tells you, where did you take it from? You took it from row 1. You took it from column 1. That tells you exactly where to put your answer. And you can see the green comes from the green matrix, the blue comes from the blue matrix. And we'll end up with 21, 8, second row, 45, 18. Now, we can multiply in both orders, right? The 2's, it's all 2's. So this time, I'll take row 1 times column 1, and I'm multiplying different numbers. Right now, this is 3, 1 times 2, 0. This was 2, 3 times 3, 5. So, of course, we're not going to get the same answers. It's going to be slightly different in every single instance. Row 2, column 2 ends up in row 2, column 2. I like the multiple colors here, not just because it's Seahawks colors. Go Hawks. Crazy moves in free agency for them, but we can multiply these, right? In order to multiply, we'll multiply component wise. Row times column ends up in row column. There might be some similar numbers in here, but there's only so many numbers in the world, like an infinite number of them, and they're close. But in general, when we multiply matrices, it's not the same. 3 times 4, 4 times 3, always 12. A times B is not always the same as B times A when it comes to matrices. All right. Let's just wrap this up. Here we go. Last two examples. Oh my goodness, we have more examples down here. Oh, the last one's really fun. It's not possible. If possible, find AB and BA. They are both 2 by 2 matrices, so we know the order is possible for both. This time, I just used the A and B as they were typed. Row 1 of A, column 1 of B, row 1, column 1. Now notice, here's an example. First of all, this is an identity matrix, right? It's square. It has 1s on the diagonal and 0s everywhere else. So when I multiply A times the identity, I just get the matrix A back. If I multiply B, the identity times A on either side, I get the matrix A back. And that's why we call it the identity. It's like multiplying by 1, but the matrix version of 1 is a little more complicated than just the number. Okay, so when we multiply by the identity, we do get the original matrix back, whether we multiply on the right or on the left. Okay, but order matters. This just shows that the identity, it doesn't matter. In general, it does. All right, number 9. If possible, find A squared. A is 2 by 2, so A squared, A times A, is also 2 by 2. So I'm going to take row 1 and multiply it by column 1 to get row 1, column 1. That's column 2, if I wanted to say it correctly. So row 1, column 2, there we go. 2 times 0, 0 times 1, right? 2, 0. And then fill in the parentheses with 0, 1. That's 2 plus 1. That's 0 plus 0, which is 0. Woo. All right, so we can find A squared. We multiply the matrix by itself. As long as it's square, you'll always be able to find as long as the matrix A is square, you'll always be able to find its square by multiplying it by itself. But if we have a row matrix or a column matrix, notice it's a 1 by 3. And I cannot multiply a 1 by 3 by a 1 by 3. The dimensions don't match. So that's adding, subtracting, scalar multiplication, and multiplying matrices. That's the first half of today's lectures.